All right, today we're diving headfirst into the really weird side of physics. I'm talking about stuff that sounds like it was pulled right out of a sci-fi movie, but believe it or not, it's all happening in real labs right now. So, let's get into it. This quote really nails what we're talking about today. We're going right to the edge of what we think is possible. We'll kick things off with a huge, tantalizing idea, anti-gravity, and then we'll shift to something even stranger, real, proven states of matter that just completely flip our understanding of the universe on its head. Okay, so let's start right there, at the edge. We're going to begin with a concept that's captivated, well, pretty much everyone for generations. It feels both totally impossible and somehow inevitable. I'm talking about the dream of actually controlling gravity. And that leads us right to it, the anti-gravity question. Can you really do it? Can you cancel out or even reverse gravity? It's the stuff of science fiction, right? Floating cities, flying cars, the whole deal. But from a science perspective, this is a massive, massive challenge. So what's the real story? What does physics actually say? Okay, the key word you really got to focus on here is hypothetical, because in mainstream science, anti-gravity just isn't a thing. It's not a proven force, it's an idea, a huge question mark that hangs over one of the most solid, time-tested theories we have. And here's why it's such a big deal. Einstein's theory of general relativity, which, by the way, we've tested and proven over and over, tells us that gravity isn't a force pulling things down, it's the shape of space-time itself. Imagine a bowling ball on a trampoline. That's a planet warping space-time. So for anti-gravity to exist, you'd need a way to, reach in and flatten that trampoline out again, on command. That's not just a small tweak, it's a direct challenge to how the universe is built. But look, that hasn't stopped people from trying. Oh no, there have been all sorts of fringe experiments over the years. We're talking high-voltage capacitors, spinning superconductors. People have thrown everything at the wall to see if they can find even the tiniest little anomaly, any hint at all that gravity isn't what we think it is. The problem? The results have been shaky, at best. A lot of the time, they can be explained away by other forces, and the big one, nobody's been able to reliably reproduce them. And this is where our story takes a really fascinating turn. The hunt for anti-gravity might have hit a wall, but all that work, all those tools they built to create extreme conditions, like super low temperatures and incredible precision, well, that work led them to stumble on to something else, something real. And honestly, it's so bizarre, it makes anti-gravity seem kind of boring. So, welcome to the quantum realm. We're about to look at two real, confirmed phenomena that just completely defy common sense: superfluids and Bose-Einstein condensates. So first up, superfluidity. The definition says zero viscosity. What on earth does that mean? Well, picture this. You stir your coffee, and it just keeps swirling forever. It never stops because there is absolutely zero friction. That's a superfluid. It's this wild state of matter you get when you cool liquid helium down to just a whisper above absolute zero. And the way this stuff behaves is just mind-bending. It conducts heat perfectly. And get this, it can actually defy gravity, but in its own weird way. There's this thing called the roll-in film effect, where a super thin layer of the liquid will literally crawl up the inside of a beaker and spill over the top, all by itself. It's like it's trying to escape. It is a genuine quantum magic show. But hold on, because we can go colder. And yes, we can get weirder, a lot weirder. If you take a gas of certain atoms and cool it down to a billionth of a degree above absolute zero, that's almost impossibly cold, something incredible happens. The atoms, they stop being individuals, they lose their identity and all merge together into one single quantum object, a superatom. They're no longer little balls bouncing around, they're one giant single wave. And actually making one of these things is just an incredible feat of engineering. So how do they do it? First, they blast the atoms with lasers from all sides. It sounds counterintuitive, but it actually slows them way, way down, which is the same as cooling them. Then they trap these super-chilled atoms in a magnetic bottle. And for the final step, they use what's called evaporative cooling. They basically let the hottest, most energetic atoms escape, leaving behind only the absolute coldest, which then collapse into that superatom state. Okay, so let's do a quick side-by-side here. Superfluidity, that's a liquid helium that flows with zero friction. A Bose-Einstein condensate, or BEC, that's a gas of atoms that merge into a single quantum wave. The big things they have in common? They both happen at ridiculously cold temperatures, and they both give us this amazing peek behind the curtain at how quantum mechanics really works.
Now, I know this all sounds super abstract, right? Like, why does this matter to me? But here's the thing. This research is so important because when you learn to control matter on this fundamental quantum level, you unlock a whole new toolbox for building future tech. This stuff is way more than just a cool experiment in a lab.
Figuring out how to create and control these states is literally paving the way for technologies we're only just starting to dream up. Take BECs, for instance. Because they act as one single quantum object, they are incredibly sensitive to their surroundings. That makes them perfect for building ultra-precise sensors that could detect tiny changes in gravity, and of course, they are a huge area of research for building quantum computers. This isn't just theory, this is the foundation for the next wave of innovation.
So that brings us to the big takeaway. We might not be building anti-gravity machines anytime soon, but what we are doing is maybe even more incredible. We're learning how to engineer the very building blocks of our universe, atom by atom. And that ability to manipulate matter at the quantum level, well, that's a power that's way more profound than just making things float. It really just leaves you with one question, doesn't it? What are we going to build with it?